So it's my great pleasure to introduce our speaker for this week, who is Srini, who's joining us from the University of Illinois, where he is currently the Center for Astrophysical Surveys, like fancy fellowship at CAPS in Illinois. He got his PhD at the University of Chile in 2016, and after that he did a couple of postdoc stints both in Melbourne and in UCLA. So he's been a longtime expert on using CMB survey data for a variety of purposes, including things from like very, very cosmology to somewhat less cosmology to, still cosmology. But so he knows way more about cosmology than I do, that's for sure. And I'm happy to have him here for us today. So I think we have maybe 1 or 1.5 more slots for dinner tonight. So if you'd like to go to dinner, please let me know or sign up on the sheet. Yeah, I think we're gonna do Mexican, but otherwise somebody else really doesn't want to do that. Okay, that's enough of me blathering. So please take it away, Srini.
Thanks, Justin. So Grace and Kevin. Thanks everyone for coming. Okay, so I'm gonna try and say what we can do with cosmology and astrophysics with the secondary anisotropies of the CMB from South Pole Telescope and future surveys. And hopefully at the end of this talk, I'll be able to convince you that the secondary anisotropies are a really good probe of both cosmology and astrophysics. Okay, so here I have a few snapshots from my talk. Sort of gives an idea of what I'm going to talk about. So I'll be heavily concentrating on how to constrain the epoch of reionisation using an effect called kinematic Sunyaev-Zeldovich signal. I'll explain what that is. And then I'll also focus on how we can use galaxy clusters obtained using this effect called thermal Sunyaev-Zeldovich effect, and use that to constrain, for example, cosmology and astrophysics. And then if I have some time, I'll also tell about how to do cross correlations with underdense regions in the universe with these secondary anisotropies of the CMB. Okay, so this is the outline of the talk. So I'll briefly explain the timeline of the universe in this time model of cosmology, then get into the CMB, both the primaries and the secondary anisotropies, and then focus on these two things that I mentioned before, KSZ and TSZ. So these things are mostly coming from overdense regions in the universe. So you observe in halo, you see these effects. But the universe is not just always overdense. There are also regions which have less halos than the other regions. And we can actually do science with those regions as well. And I've been exploring that recently. So if you have some time, I'll show some results there. Okay, so I think this is the third CMB talk. So last week I think there's Darcy. So, but I still have some introduction for CMB. Hopefully it's not overwhelming, but I'll try to move fast here. Okay, so this is the timeline of the universe. You might have seen different versions of this particular picture. I wanted to show this particular picture because I think it actually emphasizes the epoch of reionization, which I will concentrate a lot also really well here. Okay, so initially, there was inflation. So there was cosmic inflation, followed by the period of hot Big Bang. Okay, so this is what we think has happened in the universe. We have really good observations to suggest that hot Big Bang did happen. But we don't have enough evidence to say that inflation happened. So that is really the goal of many upcoming CMB telescopes, including the current ones that are observing the CMB. So in fact, detecting these primordial gravitational waves from inflation is really called the smoking gun of cosmic inflation. And this is really what many of the current and future surveys are going after. And my PhD thesis was also on that. Okay. So then what happened? So for the initial 400,000 years, the universe was just extremely hot. And as a result, it was opaque. Okay, so photons cannot travel freely. So the mean free path was extremely small, that if a photon tries to travel, it interacts with an electron and it changes its direction. So pretty much what happens inside our sun. This keeps happening for 400,000 years. But during this time, the universe is expanding. And since it's expanding, it's also cooling down. And around 400,000 years is when the temperature is cool enough that neutral atoms can form. So we now have hydrogen in the universe. Okay, so 400,000 years, then we have this period called dark ages because it's just hydrogen and pretty much nothing happens in the universe. And then later, with time, something happens. So these halos are collapsing under their gravity, and they're starting to form structures. So first we have these stars and galaxies forming, and these stars and galaxies, these are emitting ultraviolet photons, and these ultraviolet photons are basically kicking the electron out from these hydrogen atoms. So universe is now going through this epoch called reionisation, because this is the second time the universe has been ionized. So this happens for a while. So that's the period when stars and galaxies are forming. And then later, as time progresses, more and more structures start to form. Okay, so we have this hierarchical clustering model where small structures form first, leading to bigger and bigger structures. Right, so we have galaxies, galaxy clusters, and the cosmic web. Okay, so but this is the epoch that I want to focus a lot on, because that's basically what I've been working on. Okay. So the CMB is really the key thing that we observed that suggests that Big Bang did happen. So it's it's really like the compelling proof of the Big Bang model of the universe. So this is the remnant radiation from the Big Bang. It was predicted in 1940s and then observed accidentally 20 years later by Penzias and Wilson. So this radiation is extremely homogeneous and isotropic, meaning the statistical properties of this radiation, any direction we look, is going to be the same. There are small fluctuations. These fluctuations are 1 part in a million. So they're extremely tiny fluctuations that we are trying to map with the current and future surveys. Okay. So this radiation is also partially polarized. And the reason for this polarization is because that is actually a time when the universe became neutral. I mean, the universe started to become neutral at some point, and then it became fully neutral. So there was a small period there when there are still some free electrons, and CMB photons, when they interact with these free electrons, it gives rise to polarization via Thomson scattering. Okay. Since the polarization is via Thomson scattering, there is no circular polarization in CMB. So this is only linear polarization. So when we're looking, for example, for B modes, we are still looking for signatures in the linear polarization, but we call that B mode because they look like magnetic fields. Okay. So the other nice thing about CMB is that the CMB is the most distant light that we see. So any direction we look, the farthest that we see is a CMB, and as a result, CMB basically interacts with everything we know in the universe. So CMB is free streaming towards us from the surface of last scattering. It is redshift around 1100, roughly 400,000 years after the Big Bang. And these photons are interacting with everything that we know in the universe. So it has interacted with first stars and galaxies, later galaxy clusters, and everything else. Okay. So what happens here is that only a small fraction of the CMB photons are basically changing their properties because of this interaction. And that interaction with everything that we know in the universe gives rise to this effect called the secondary anisotropies on CMB. So the primary anisotropies are the one that basically, that these are the perturbations in the primordial universe. But then things happen in the universe later, and those interactions are seen by these CMB photons. Okay. So as a result, you can actually use CMB as a backlight to study everything in the universe. Okay. So that's why CMB is really nice. So besides learning the origin, CMB also serves as a backlight to study both the contents and the evolution of the universe. So you can learn about structure formation, we can learn about reionization, we can learn about, we can detect galaxies, we can detect galaxy clusters, and so many other things that we can do with the CMB. Okay, so cosmic microwave background can be used to study the initial moments, the contents and the evolution, and also structure growth in the universe. Here's a really beautiful compiled map of the CMB observed by 3 different satellites. So first was on the left, it's COBE. So this is one of the satellites that was first launched to actually detect these anisotropies in the CMB. So you see there are some hot spots and cold spots, but the angular resolution is really poor. Okay, so I think it had something like a few degrees angular resolution. And then a decade later, WMAP was launched, and you can see the improvement in the resolution there. But there was still a few tens of arc minutes. And then later, as you might have all heard about this experiment, so this is Planck. So this is the recent satellite that was, that we have constraints from. So here the resolution has improved further, but even here it's actually like few arc minutes, right? So this is something like 6 or 7 arc minutes. Okay. So what do we actually do as cosmologists? So we map the temperature on the sky using millimeter wave observations. Okay, so we map these fluctuations and we make maps. So this is basically just an image. And then all we do is take the Fourier transform of that image, square it, and then do a radial binning. So that is basically the power spectrum. Okay, so it's actually very, very simple. I mean, there are complications when we do it with real data, but in principle, that's all we do. So you can do this with Python, right? So you take the image, you take the Fourier transform, square it, take the absolute value. That's the power spectrum. Okay. So we have the power spectrum. So those are the data points. So now we try to fit model curves to this, and the model curves, the parameters for these model curves are the lambda CDM parameters. Okay. So this is basically how we come up with the standard model of cosmology when we do this with CMB. So we can do this independently with CMB, or we can also combine this with external data sets. We can combine this with supernovae. We can combine this with galaxy clusters and BAOs and several other things. And this is really how we establish the standard model of cosmology, which is this lambda cold dark matter model. Okay, so why can we do this? So this is a paper that was actually led by Kevin. So this plot basically shows how good CMB is in detecting different things in the universe. So this is called the power spectrum. So it's very similar to the plot that I showed before. And I'm going to show a lot of these kinds of plots. Okay. So what this is it's simply just a 2-point correlation function. Okay, but in the angular space. So we have an image. So now you take 2 points. So you have an angular separation to these 2 points. You calculate the correlation function. You now just shift this here, shift this here, shift this here. Basically take the mean of all of those things. And that is, so you're taking the mean as a function of angular scale. So now instead of this triangle, you actually shrink it. So now the angular scale is different. And then you make more and more data points. And similarly, you do it at every scale. And then you plot this, right? So the horizontal axis here is the angular scale. It's actually the inverse of the angular scale. So this is the spherical harmonic transformation. It's called the multipole. So when you're looking at left side of this plot, we are looking at really, really big angular separations on the sky. And when you're looking at the right side, we are looking at extremely small angular size. So for example, this bump here, so the bump actually corresponds to roughly 1 degree on the sky. The reason it corresponds to 1 degree is because that's roughly the size of the horizon at the time of recombination. Okay. And then when you're looking here, you're looking at arc-minute scale separations. Okay. So the vertical axis here is basically just a power, so it's just the variance in real space. So now you can see, you measure different portions of this power spectrum, you actually infer different things. For example, with the first peak, you can learn how if the space is curved or flat. And if you're looking at these smaller scales, you can actually learn a lot about relativistic species in the universe, like neutrinos. Okay, so this is with temperature. But I also told you that CMB is also polarized, but it's only polarized to like roughly 10% level, so the amplitude is much smaller. Okay, but this polarization also has lots of cosmological information. Okay, for example, again, if you look at this region, you can learn about the relativistic species. But then if you look at that region of the polarization power spectrum, we actually learn about reionisation. Okay. So then we also have this curve. So this is basically the B mode power spectrum. So this is the E mode power spectrum, which looks like electric fields. But when you're looking at B mode power spectrum, you can learn about structure formation here, and then you can learn about inflation there. Okay. So these curves, you can only see one curve, but here we have 3 curves because we actually don't know which of these actually correspond to inflation. So maybe none of those correspond to inflation. Okay, it's probably even smaller. Okay, so you can map the sky, you can compare this power spectrum both in temperature and polarization, and you can learn a lot about cosmology. Okay, so that's why this is key. And this has been done by several experiments. Okay, and here is basically a compiled plot from all of these experiments from the CMBS4 collaboration. Which again, Kevin, you might all know that Kevin is the spokesperson of CMBS4. So this is basically showing data points measured by different experiments, and then also showing a curve that goes through all these data points. Okay, so this curve obviously looks like a really, really good fit to all these data points. Great, but I want to emphasize that this curve is actually not a best fit for all these data points. This curve is actually a prediction from Planck. So Planck has observed CMB, Planck has come up with the lambda CDM model. And then you take the curve, you take the prediction, and then all these other experiments lie perfectly on this curve, right? Which is great, right? So, but then there is definitely some deviation here, okay? Which is because of the secondary anisotropies, and I'll get into those details, okay? So this is great, okay? So if this is great, why are we still doing this science, right? So we have lambda CDM, and all the data points are just aligning really well with lambda CDM. So then why do we have to build new surveys? The reason we want to do this is because there are so many mysteries. So this lambda CDM model has dark matter in it. It has dark energy in it. It has gravitational waves. It has neutrinos. And we do not know the properties of many of these things. We actually don't know a lot about these things. But somehow this lambda CDM just works. Right? It's actually a mystery. So we don't know how it works. That's why we want to build these new surveys to understand what these things are. And then there are also tensions. So for example, we have constraints on Hubble constant from CMB surveys. We have constraints on Hubble constant from supernovae surveys. And you might all know that they are in tension by more than 5 sigma, right? So this could be some physics, some new physics that we are missing. This could be some systematic in one of the data set. Similarly, there are also tensions in structure growth, okay? So this is basically a tension in a parameter called S8. So CMB telescopes are giving us a measurement of the structure growth parameter. Galaxy surveys are giving us a slightly lower value of this. So this could be, again, real physics. So this could be feedback. This could be gastrophysics, or this could be a systematic. Okay, so these are all the things that we want to probe. That's why we want these new things.
Can you remind me why the E mode cuts off below like L20? If you go to the very large scales, like we just haven't measured the epoch polarization at those very large angular scales.
So we have measured. I don't know why those things are not plotted, but we have measured. So that's in fact where our constraints on reionisation actually comes from.
So
that's basically like the Planck points. Right. Yeah, we have measured. Yeah. Okay. All right. Okay. So that's where, so these new surveys and the current surveys. So that's where all these things come into play. So SPD is South Pole Telescope. So that's the experiment that I'm part of. So that's obviously in South Pole. Okay. As you can see from the image. So then we have Atacama Cosmology Telescope, which is just been completed. So that's in the north of Chile, roughly 18,000 feet above the sea level. So then pretty much in the same place we have Simon's Observatory. It's just starting. Okay, it's just starting. So it's another amazing CMB experiment that we are all looking forward to. And then CMBS4 is really like the next generation CMB experiment where everyone working in the field of CMB in USA are part of. Okay, so we are all combining together and we are coming up with this experiment, so in this image you see both South Pole and Chile, but there is some flux there right now, so we don't know what it's actually going to be, but we definitely hope this happens. Okay, so this is South Pole Telescope. Okay, so this is a really amazing photo of the South Pole Telescope taken by our winter rover, Aman, was a PhD student in Melbourne. So this is basically like a time lapse of an eclipse. Okay, so you just put the camera there, and then you just record it, and you can see that. Right? So this is just amazing. I think it was also like one of the astronomy pictures of the day or something. So here is the South Pole Telescope, and you see Aurora Australis there. So these are like common things that you see there. Okay, and you can also see the sky. Sky is great. So South Pole Telescope is a 10-meter diameter telescope. Okay, so for people doing optical astronomy, this may not sound really good. The angular resolution is 1 arc minute, which is the best that we have in radio. Obviously, that's very, very coarse compared to many other things that you might all have been thinking about. But nevertheless, you can do a lot of really good science with SPD and also ACT, which is pretty similar angular resolution. Okay, so it's observing from the geographic South Pole in the millimeter wave bands. And this is roughly the configuration of South Pole Telescope. So right now it's in its 3rd generation, so we call it the SPD-3G. Previously, 2007, the 1st generation was launched, so it's called the SPD-Z survey. And then later, we have polarization sensitive detectors, so it's called the SPD-Pol. And right now we are in a 3rd generation where you can see, for example, between the 1st and the 3rd generation, the detector count has actually increased by an order of magnitude. Means we are way more deeper than we were before. So we observe in 3 bands, so 90 gigahertz, 150 gigahertz, and 220 gigahertz. The resolution is roughly an arc. Okay, so this augmented resolution is actually great, which you'll see in these images. Okay, so this, for example, is a real image taken by this WMAP satellite. So it's roughly 30 square degrees. Okay, so you see this image, it's very coarse, right? But you do see like hot spots and cold spots. So you see some dark regions and bright regions. So these are all really CMB. Okay, so the size of these blobs roughly correspond to 1 degree, which is because that's really the size of the horizon at the time of recombination. So now, if you look at the same region with Planck, you can see that the resolution has improved, right? And the noise level has also improved, right? But now, if you look at the same region with SPT, this is what we see, right? So we don't just see the CMB now, but we also see these, tiny spots, right? So these bright spots, these dark spots, right? So this is basically because of the resolution and the noise level, okay? So the majority of the thing, the large scale features are all CMB here. But if you're looking at these tiny spots, right? So these ones, so these are basically galaxies, right? So these are galaxies which also emit in the same band as we're observing. So these are quasars, AGNs, or high redshift dusty star-forming galaxies. So for us, right? So for me, these are contaminations. Okay, but these are really the signal for Justin. Right. So basically, we take these things and then people do follow-up observations, and that's how you get those kinds of really beautiful images. Okay, so those are galaxies, but you also see these dark spots, right? So these dark spots are actually clusters of galaxies, right? So the reason they appear dark is because of this effect called the Sunyaev-Zeldovich effect. So they appear as shadows in our image. And I'll tell you what that is, what that effect is later. Okay, but the single dot actually has like so many galaxies in it. Okay, so we also observe those, right? But currently SPD is so sensitive that we don't just see these things. We also actually see asteroids, and we see like Starlink satellites and everything. Okay, so it's good to build these really amazing highly sensitive issues, but then we are also having all these other issues. Okay, so just want to show this. So this is basically where we observe. So the green patch is our main field. So it's 1500 square degrees. And then during summer, so this is austral summer, roughly November to February, sun basically passes through our field, through our green field. So then we observe this additional region called the summer field. But then this year we also did this really wide observation, so which roughly is 6,000 square degrees. So in total we have something like 10,000 square degrees. Okay. So that's what we have in SPD. And you can see it has really good overlap with other CMB surveys, like for example what SO is going to observe. So there are like lots of good cross correlations that we can do. And then we are also overlapping with lots of other deep fields like Euclid and SphereX deep fields. Okay. And then this map here. So this is a map from just 1 week of observation. So basically, SPD3G can reach the same depth that Planck has reached in just 1 week. So Planck has observed this for the sky as for several years, but SPD3G in this 1500 square degrees, in 1 week we can reach the same depth. But we have roughly 5 years of observations, so we are way more deeper than Planck, but in a smaller patch. Okay. So as a result, we have lots of science cases. So this is pretty common for a few other CMB experiments as well, like SO, for example. So we do inflation science by combining SPD with another telescope called BICEP. We can do cosmology with CMB. We can constrain reionization using CMB. But then we also constrain cosmology and detect these high redshift galaxy clusters and galaxies and asteroids and everything. Right. Okay. So now let me just get into the secondary anisotropies and tell you how amazing these things are. Okay. So now these CMB photons are free streaming towards us from the surface of last scattering, and then on their way there is matter everywhere. Right. So we have galaxies, we have halos, so there is matter everywhere. So the path of the CMB photons are getting bent. So this is gravitational lensing, as you might all have known. And this has been observed with very, very high significance currently. So that's the first effect. The second effect is this effect called the thermal Sunyaev-Zeldovich effect. So this is the reason why those galaxy clusters were appearing as dark spots in our image. Okay. So this is inverse Compton scattering of CMB photons because of free electrons. So what's happening here is that, so imagine you're observing this region with a telescope from there. Let's say that the telescope is observing at this 150 gigahertz. Okay. So CMB photons are coming towards us from here. But then imagine in the middle, you have a galaxy cluster. So galaxy clusters are normally hotter than average. So if something is hot, they should have free electrons. So what happens is the CMB photons are going through this galaxy cluster. So first they get lensed, but then these CMB photons now get an upscatter because the free electrons are interacting with the CMB photons. So they gain energy, they just shift to a different energy band. Okay. So as a result, in this 150 gigahertz, you see a decrement because those CMB photons are now just gained energy and moved to a different frequency band. They have been upscattered. So for us, it looks like there is nothing in that location. Okay, so it looks cold for us, but it's not really cold. It's just because of this effect called the thermal Z effect. Okay, so this is what we use to detect galaxy clusters. But there is another interesting thing, which is that so there are these free electrons, but these free electrons are not just static, because everything in the universe is always moving. So if these free electrons are moving towards us, the CMB photons are now getting a Doppler blue shift because these things are moving towards us. But if the CMB photons are moving away from us, CMB photons get a Doppler redshift. Okay, so in a given location, if there is a halo moving towards us, and if it has free electrons, the CMB will look brighter. But if the halo is moving away from us, CMB will look dimmer. Okay, so this is called the kinematic Sunyaev-Zeldovich effect. And it's kinematic because it's related to velocity. Okay, so it's related to electron density and it's also related to velocity. So you have some electrons, but these electrons are moving. Okay, so it's proportional to both velocity and the electron density. Okay, so now basically those are the three effects, and these are the reasons why there is a deviation here. Okay, so we see some deviation. So so this curve is just lambda CDM. It has nothing to do, it is not predicting the number of galaxy clusters and everything. So we have galaxy clusters, we have galaxies, we have these other effects, so that's why there is a deviation here. Okay. So now let me get into this and let me tell you how we can do reionization science with this. Okay. So like I said, kinematic SZ, so this is Doppler boosting of CMB photons due to free electrons, but in motion. Okay, so these electrons are always there and the electrons are always moving. So there are two sources for this. So one is in the local universe, halos, we have clusters, we have clusters of galaxies, we have galaxies, they have electrons, and they're all moving. So we have a low redshift component, and this is basically due to matter inhomogeneities in the universe. Okay. But then when we go to higher redshifts, so we have this process called the epoch of reionization, where the universe is being reionized due to stars and galaxies. But this is happening in different locations at different times. So these are like bubbles of electrons. So these are patchy bubbles of electrons in different locations of the universe. And they're all moving either towards us or away from us because of the cosmological velocity flow. Okay. So there is a high redshift piece and then there's a low redshift piece. So this low redshift piece, you can detect this by cross-correlating our data with galaxy surveys. It's hard to do it for high redshift because we don't have high redshift galaxy catalog, like redshift 8 or 9, right? So obviously that's much harder to do. So this is due to patchy reionization. What this is, so this is basically the period when light from the first stars and galaxies are reionizing the hydrogen in the universe. There's actually another epoch where helium is also reionized. So these are UV photons from these stars and galaxies that are just kicking the electron from the neutral hydrogen atom. Right? And then here is a simulation showing how this process would have worked. So you see everything is just dark because it's just neutral hydrogen. But then you have these pockets, these patchy bubbles. As time progresses, you will see that these patchy bubbles are now growing. Okay, because there are some regions that are reionized first, and then these bubbles are growing, and then finally, when the universe is completely reionized, this process will eventually stop. Okay. And you can see over time, these bubbles are coalescing and forming bigger and bigger bubbles. Okay. So this is basically the epoch of reionization. So how can we study about this with CMB? You can actually use like few different methods. So one method is really simple. So we have free electrons, we have CMB photons traveling towards us. So now imagine a cloud of electrons. So this cloud of electrons is going to have an higher optical depth. As a result, the light is going to be attenuated. So it gets attenuated by e to the minus tau. So in power spectrum, it gets attenuated by e to the minus 2 tau. So this is very simple physics, right? But it's very hard to observe this because this suppression is completely degenerate with the normalization of the power spectrum. So you can say, I'm shifting the normalization up or down. If I shift the normalization up, I can increase the optical depth, which will shift the power low, right? So it's very degenerate, so you cannot really do anything with that. The second is basically the signal coming from polarization. So this is the question that Justin asked before. So at the time of reionization, so universe is being reionized, so you have more free electrons now. So since there are more free electrons, we have additional polarization that are being generated in the universe. So there was polarization that happened around recombination, and then universe was neutral. Then around reionization, we have new free electrons, so we have more polarization. But at this time, the size of the universe is much bigger. So that's why there's a bump on those extremely large scales. Okay, so Planck has measured this, and that's how we have we actually know what is the optical depth of the universe. However, Planck is completely insensitive to how the reionization actually happened. So what you can see here is that on the right, so you see the same thing that I showed. Okay, but now on the left, we are seeing the reionization history of the universe. So the horizontal axis is redshift. Vertical axis is basically saying if the universe is neutral, then 0, or completely ionized, which is 1. So now you see there are different curves, including some really funny curves where you can see that this sine curve increases, decreases, it goes up again. But you take all those curves and then you predict what the E mode polarization is going to be. They are all just lying on top of it. And within the error bar. So even though we measured this, there is no way of knowing how reionization actually happened in our universe. So that's why we want to move beyond this. And that's where the kinematic Sunyaev-Zeldovich effect comes into picture. So here, for example, I'm showing how the 2-point correlation function of KZ is sensitive to reionization. So this is a plot from simulation. So you have 3 simulations. So it's, the box size is roughly 200 square degrees. And you can see based on how the process actually happens. So for example, there you see a lot of small scale structures, like lots of fine grains. So basically that changes the power spectrum of the KSE. Okay. But I'm highlighting the extent of the y-axis here. So you see, so this is in microkelvin square, and it goes from 0 to 4, and it's a linear scale. Okay, so there is a reason I highlighted that. The reason is because KSE is actually not the only thing that we see in our data. In fact, KSE is the dominant. It's the least. It has the least amplitude of everything that we see. So KSE will never be observed with a signal to noise greater than 1 with any feature surveys, right? So this is just impossible. So what I mean by that is when we look at a map, by eye we cannot say that that's KSE. So here you can see that these bubbles, these are KSE, right? But you'll see in the next slides that that's just not possible. But statistical detection is possible. So statistical detection is in fact like 100 sigma with the feature stories. Okay, so now let me just show you what I meant by that. Okay, so now in the previous axis, so in the previous plot, so the scale was going from 0 to 4 in linear scale, but now you see it goes from 1 to roughly 500, right? So few orders of magnitude. And that's what KSE is. So that is a map. So this is a simulation. So you see KSE there, right? But now if I add noise to this, so you see that KSE is just gone, right? And you can see that noise is much larger. And now if you add all the astrophysical signals like clusters and galaxies and everything, now that's all gone. Now if I actually add primary CMB to this, that's how things look. So if we just add everything, that's basically how this looks, right? So if I just flip between these two things, so you see, we basically just see CMB here, right? So you can do some filtering to get rid of CMB, but here you see on small scales, this is still contaminated by all the other things, right? So this green curve can never be measured with signal to noise greater than 1 because all these other curves are above the green curve. So doing this is hard, but SPD, yeah.
What do you mean by small scales? You mean
So these are arc-minute scales.
Okay.
And
Yeah.
why is the power spectrum flat for KZ?
Yeah. So the power spectrum is actually not flat, but I've plotted them in this unit so that it looks flat, right? So this is not just the power spectrum, but this is power spectrum times a funny unit. So this is like L square. Yeah. Okay. So a couple of years back, SPD released the results where we had a 3 sigma measurement of KZ. So some people call it 3 sigma detection. But 3 sigma, it's not clear if it's a detection or if it's just an evidence. So what you're seeing here is the auto power spectrum and cross power spectrum of the 3 SPD bands. On the top panel, you see 90, 90, 150, 150, 220, 220, and then the bottom, you have the cross correlation. So we have the data points here. And then you have different curves. So KZ is basically this blue dashed line, which is going to be the same in all the frequency bands because it has no frequency dependence. But you see, that's basically like very, very subdominant compared to many other curves. Particularly this curve, which is basically signal coming from dusty star-forming galaxies, several orders of magnitude larger. So if you get this curve wrong, everything about this is going to be wrong, right? So we have to be very careful when we do this. But nevertheless, people used our results and tried to constrain reionization. For example, this is plot from simulation, trying to constrain the midpoint of reionization and the duration of reionization. So obviously you can see 3 sigma is just consistent with everything, right? Because it's only 3 sigma. It's not constraining things significantly. So now the question that we wanted to ask is, so KZ, like I said, it's actually a patchy process, right? So I showed this image. So the main thing that I want to emphasize here is that you have these bubbles, so it's very non-Gaussian. So when something is very non-Gaussian, we don't have to stop at power spectrum. That is information beyond the power spectrum. So what I mean by that is, if you take our map and if you just histogram all the points, if you just histogram all the pixels, in the Gaussian map, it'll basically look like a Gaussian, like a bell curve. But if something is non-Gaussian, it'll have a skewness and a kurtosis to it, right? Which means it's very non-Gaussian. That's how a KZ map will look. We have to go beyond the power spectrum. And it has some nice things to it. So this is called the tri-spectrum of the KZ. So this is no more power spectrum, because power spectrum is 2-point correlation. Tri-spectrum is 4-point correlation. So we are trying to figure out the correlation between 4 different points in the sky. So the reason we want to also do this is because it also nicely separates the contribution from these 2 KZ components. So the high redshift piece and the low redshift piece. Because in the power spectrum space, it's really hard to distinguish between the two. So what you're seeing here in this particular plot is that it's a derivative of this tri-spectrum. That's the vertical axis as a function of redshift. And you clearly see it's bimodal. It's bimodal because there are two KZ sources. So this one peaking around redshift 8 or 9. So that's the reionization KZ. And this one that's peaking in the low redshift, so that's the local KZ. So what you see here is that the high redshift piece is much more brighter than the low redshift piece. Meaning, if we take the tri-spectrum of the KZ, we are just going to see the contribution from this high redshift piece, which means we are only seeing reionization KZ. So we tried to do this recently with SPD. So we built this estimator, which is very similar to CMB lensing, if you know about it. So what this is basically doing is that we have matter inhomogeneities. So this is at the time of reionization. So you have some clumps here, you have some clumps there, you have some clumps everywhere. But all these clumps, they're all being modulated by a really, really long wavelength velocity mode. So they're all moving because of the velocity in the universe. So there is a very long wavelength correlation between all of these small scale clumps. We can use that information to actually reconstruct velocity in the universe. So we did this. So for example, on the left side, you are seeing simulation, on the right side, you see data. So the only thing that I want to emphasize here is that the statistical properties of these two look pretty similar. So you see some cold blobs and hot blobs. The number of cold blobs, number of hot blobs are roughly the same in both, which says that we actually understand our data. And then if I actually plot the tri-spectrum, it looks like this. So horizontal axis again is the inverse of the angular scale. Vertical axis is the tri-spectrum. So the green is basically our data points. the violin actually shows the scatter in 100 simulations. You can see our data is very consistent with SIMS, which is what we see in the which you saw in the previous plot. However, unfortunately, the SIMS that we have here actually have no KSE in it. Right? So what that says is that what we are seeing here is not KSE. We are actually seeing contamination from many other things. So we didn't measure KSE. So there is really no KSE because if we take this mean black curve from SIMS and if we subtract the green points, you see everything is just consistent with 0. So there is no detection. But that's not all. So we can actually use this no detection to constrain reionization. Because if reionization happened with some particular properties, we expect some KSE. But the fact that we don't see that means that we can remove some models, we can exclude some models. So we can now do that with this is from KSE alone. So the vertical axis is basically the midpoint of reionization. So that's the redshift at which the universe was 50% reionized. On the horizontal axis is the duration in terms of redshift. Now you see this is not looking really nice. So they are both very degenerate. So KSE is not doing much here. However, that's not the story, because we actually have observations of high redshift galaxies and Lyman alpha forests, which gives us some hint on the reionization process. So in particular, if I make this plot again, so this is redshift on the horizontal axis and vertical axis is the reionization history. So you see at around redshift 10, we have this high redshift observation, which says that the universe is actually just neutral, right? So you know, there's been some debate about how well you can trust these data points, but nevertheless they exist. So then you have these slightly lower redshift, and you can see that the reionization is actually increasing. So then this point is the key. So if we come to redshift 6 or 5, basically all of them are pointing to the fact that universe is just completely reionized. So this is called the Gunn-Peterson trough. It says that the universe should be reionized around redshift 5 or 6. We can actually use this information and do better things. And this is what we did. So this is what we got from our paper. And you can see that's actually really consistent with all the other data points. The reason it's consistent is because the error bar is slightly larger. Okay. So now the question really is for the future is like where will these high redshift observations from JWST will lie? Because I think people are already starting to find discrepancies with the high redshift galaxies. We are having more galaxies than expected. So there is already a tension here. So now we did use that information. So we used that information as a prior. So we said, so we have this black curve from KSE alone, but then we know universe is reionized around redshift 5 or 6. And if we do that as a prior, it basically excludes all this region out. So now we are now in this particular region. And in that region, so we actually, just with this non-detection, so we don't have a detection, but we already were able to constrain the duration 2 sigma to less than 4.5. So that's in the redshift width. And then we did this independent of Planck. So we just didn't use Planck here at all, but our results are actually consistent with Planck. So finally what this is saying is that it's actually ruling out very slow and early reionization models, right? So we don't have a detection, but we are already able to do this. But in the future, things are even better, right? So this is basically a forecast combining KSE and Planck for different instruments. So on the left, you see the constraints on optical depth of the universe and the duration of reionization from KSE to 2-point function. So that's the KSE power spectrum. Then in the middle panel, you see the KSE tri-spectrum. So what you can see here is that KSE does not really constrain optical depth. But the nice thing is that the direction of degeneracy is different for these 2 panels. So when you combine these and when you add Planck, it looks actually really good for CMBS4, for SO, for SPD. So our 2 sigma limit was 4.5. But you can see with the future, we can actually get down to actually 1 sigma 0.5. So this is really great. Yeah.
Maybe naive question. So why we don't have 3-point function?
Yeah. So we won't have 3-point function. We don't have any odd points for KSE because KSE is moving. That could be things moving towards us and away from us. So if you just stack everything, you get 0. So all the odd points vanish for KSE. So you can only do 2-point, 4-point, 6-point, and so on.
The other thing that we can actually do is cross-correlate with with galaxy surveys, where you use an information on velocity. So if once you know halo is moving towards us, you can use that information to construct the 3-point function. But internally, we cannot do that because it's just 0. Because some halos move towards us, some halos move away from us. So average is to 0. So only the even points exist. Okay, so that's basically yeah. So now Casey is also here, and I already finished KSE part introduction earlier. Okay, so now let me spend the next maybe 10 minutes in talking about TSE and how we can actually do some gas physics with this, or feedback physics with this. Okay, so I told you that we detect KSE using the thermal SZ signal, right? So that's why it appears as these dark spots, right? So this is the inverse Compton scattering. So the nice property of this is that this effect is actually independent of redshift. So a cluster at redshift 3, if it exists, or a cluster at redshift 0.5 will pretty much look the same for us. Whereas when you take an optical survey or an infrared survey, flux is dropping when you move to higher redshifts, so it's very hard to detect these high redshift clusters. So that is the advantage of using CMB surveys to detect these high redshift clusters, but it is also the disadvantage because we have no information about the redshift. So we have to do some cross correlation to get their redshifts. But we can detect them. So this is, for example, an image showing that frequency dependence that I was talking about before. So this is from Planck. So Planck has actually already observed this. So you see at this 140 or 150 gigahertz, you see a decrement. And if you go to like lower frequencies, you see more decrements. At 217, actually nothing happens. So the cluster is just invisible at 217. And if you go to these higher frequencies, you actually start to see an increment. So this effect is very frequency dependent. But this is how we detect clusters. Okay, so this is a plot from CMBS4. It's basically just showing. So the vertical axis is basically the minimum mass of the cluster that we can detect as a function of redshift on the horizontal axis. So what you can see is about redshift 1.5 or so, we can basically get down to halos that are less massive than 10 to the 14 solar mass, right? Which we were never able to do before. And then if we just convert this into cumulative redshift distribution of all these clusters, we see this. Right? So the current samples are all there. So the vertical axis is the number of clusters, cumulative distribution. Horizontal axis is redshift. So you can see with these future surveys, we are actually going to detect some 100,000 clusters. Particularly at these high redshifts, we are going to get like few thousands if they exist. Okay. So we don't know if they exist, or we don't know if they are virialized. But if they are virialized and if they exist, we are going to get them. Okay.
So this is from like a dark matter only simulation kind of prediction, or this includes that effect of do they have a hot ICM?
This is only dark matter simulation. I actually have a different plot, but I just removed it. But yeah, but it seems that we can actually constrain that with these.
Statement about virialization, right?
Yeah.
Virialized and have a hot IG.
Yeah, which is what you need for the SE.
Yeah. Right. So if the clusters are completely not virialized, there's going to be a break about redshift 2, which is also interesting, but I don't think it'll be like that.
We'll find out, I guess.
Yeah, we'll find out. Okay, so I just want to show this schematic to show why clusters are a good probe of dark energy. I'm doing 2 simulations. Okay, so this is the cosmic web that you're seeing, and then you're seeing these yellow spots. So these are basically clusters sitting at the node of these filaments. So statistically speaking, both these panels at redshift 0 have roughly the same number of yellow circles, but one of the simulation does not have dark energy in it. So it's very hard to distinguish between the two. But if you actually go to high redshift, you go to redshift 0.6, now you start to see a difference between the two, right? Now, if you go to even higher redshift, there is a clear distinction between the two. So these high redshift clusters are key. And the reason this happens is because clearly this is the simulation without dark energy. You might have all guessed already. So in a universe without dark energy, these structures can form almost immediately. So all these yellow circles are forming in the relatively low redshift universe. Whereas in a universe which has an influence on because of dark energy, where things are actually expanding, it takes more time to form these things. So you need a lot of time to form these structures. Okay. So that's why if you detect these high redshift clusters, you can actually learn a lot about dark energy. But we can learn more from this. So forget about the individual clusters, okay? But you can also compute the power spectrum of all of these things. So we call the thermal SZ power spectrum. So this is pretty much the same thing that I was talking about, but this is only for the thermal Sunyaev-Zeldovich effect. So now you see those points. So those are measured by Planck on the large scales. But then you see these points that are measured by ACT and SPT on small scales. So clearly, that prediction is not matching any of these things, right? So that is some inconsistency between the large scale observations and small scale observations. So this again could be real, or this could be an artifact. So if this has to be cosmology, so what I'm now doing is trying to change cosmology. So basically just changing the amount of neutrino mass. And you see it still doesn't fit really well, right? So maybe this red curve is okay, but that is like enormous amount of neutrino mass, which has been already ruled out. And you can also see that changing this, it's mostly just shifting the normalization. So now you can actually change feedback, okay? So what happens is that, so we have these clusters, right? But then when you have feedback, when you have AGN feedback, it's basically pushing the gas away from the cluster center. And that is actually reducing the small scale power spectrum. So here you have three versions. So for different versions of the feedback, high, fiducial, and low. And you can see again, it doesn't really match. So something is definitely happening here. So this is not, just within TSE, right? So this actually has implications for structure formation, which is this S-side tension that we have been seeing in the recent past. So what is S-side tension is that, so S-side is a parameter which is basically a combination of sigma 8 and omega m. So CMB surveys has observed this particular value, but galaxy surveys are observing always a lower value. So the reason it's happening is because galaxy surveys are actually probing small scales. And small scales are really the location where baryons have more effect. And by baryons, these are just feedbacks. So if we don't understand the feedback, our model is incorrect, which means our interpretation of cosmology is incorrect. So in fact, when the galaxy surveys, when they start to exclude the small scale information, you see that these data points are actually moving to the right. So this could just be baryonic feedback. But in fact, a paper actually came out. Well, last week there was a paper from ACT, but last night a paper actually came out showing that just the feedback cannot really explain all of these things. So it is a paper led by Ian McCarthy, if anyone wants to take a look. But yeah, it basically came out last night. Okay, so the reason I want to show this is because we clearly just don't understand the baryon distribution. So this, for example, is showing the ratio of the power spectrum in an universe with baryons and without baryons. And there are different simulations, and all these simulations are just, they are all different, right? So what I'm trying to say with all these things is that, so this is an analysis that we are currently doing with an SPD, and that these are the expected error bars. So you can see that these error bars are clearly going to rule out, if we detect this properly, clearly going to rule out these other models of feedback, right? So that's current. And that's future. So you can see the reduction in error bars, right? So basically with these future observations, I think we're just going to rule out all the simulations that already exist, and we're going to probe, like new things, right? Which is actually great. Okay, so that's TSE. So I think I'm just going to show maybe like two or
Is it not some combination, like if you are they additive? So if you add a higher mass neutrino plus and feedback, to shift.
Yeah, exactly. So that's exactly what you're trying to do right now with this particular setup. So you're trying to tweak both cosmology and the feedback level to see if something is matching. But honestly, I think what's going wrong here is that, so there is feedback, but there could also just be contamination in these data points. So this is probably just contamination from dusty stuff from galaxies.
We're just pulling down.
It's always the CIV.
It's Justin. When you say baryonic, when you say baryonic feedback, is that just basically saying that the baryons act and pull the dark matter with
Exactly. Well, pull the gas out, right?
Gas out.
Yeah.
Okay.
Right. So TSE is very sensitive to that. so is cosmic shear, and so is cosmic shear across TSE and also KSE.
Changing the properties of the hot gas, that would be causing a signal.
Exactly. Okay, so that's TSE. Maybe I'll just show like maybe 3 slides about this, because I think this is something really exciting. Okay, so I've been talking about all these halos, right? So halos generating KSE, TSE, lensing, everything. But now we also have underdense regions, right? So we have regions where we observe like lower density of halos compared to the mean. And so this is a simulation of how these regions will look in a dark matter only simulation. Okay, so this is lensing. So if you just take all of those locations and if you just stack them, so this is a cross power spectrum. So it's stacking is basically just the cross power spectrum. It looks like this, right? So you definitely see a decrement in the middle. So because these are underdense regions compared to the mean. But actually, if you try to distinguish this based on the overdensity parameter of these voids, you actually see different signals. So there is a family of voids which has this really large negative depth. There is this family of void which is basically like a donut. So now you can imagine if we stack this and this together, we are losing information, right? Because these hot things are basically filling this cold thing, so we are diluting the information. So what we tried to do in this paper a couple of years before, 3 years before now, is try to do this analysis by just cross-correlating Planck and cosmic voids from SDSS. Okay. Okay, so that's the suboptimal panel where we just take all the things and put them together. But now this is what we get when we do this individually. So now you see that the data points and the theory predictions are actually like pretty evident. And just by doing this particular operation, we improve the significance from 3 sigma to 5 sigma, right? Which I think is very obvious, because in the previous panel you're saying we were seeing that when we stack all of these things together, we are diluting away the information, right? So this is dark matter, right? But now what we're trying to see if we can actually do this with baryons. So those are the simulations of dark matter only, and then this is a simulation of the thermal SZ signal, and you can see they look very similar to each other. Right? So then these are the data points. So this is basically already published. So this is basically what we see right now. These are again Planck and SDSS. So we see very similar behavior between the two. So what we are thinking is, if we actually detect this with very high significance, we can try and see how baryons actually trace dark matter, at least in these underdense regions. So the underdense regions are kind of nice because most of the things are still linear. They're not very nonlinear compared to like other locations. So, I mean, it's still a matter of debate about how well we understand these regions, but this is something that we should all be thinking to do with future surveys. Okay, then that's it. I'm gonna summarize. Okay, so the current and future surveys are all great particularly for small scales. There's a lot of opportunities just internally within CMB, but also with cross correlation with galaxy surveys and with intensity mapping instruments. So with KSE, we had this constraint on the duration with the tri-spectrum, with the non-detection of the tri-spectrum, with 2 sigma 4.5. But the future looks really promising when we combine power spectrum, tri-spectrum, and Planck. And then similarly, when we talk about TSE, the future surveys are going to give us a lot of high redshift galaxy clusters. But beyond just galaxy clusters, we can look at the diffuse portion of the TSE power spectrum, and we can actually constrain feedback, and we can learn about SI tension. And finally, there's also voids in the universe, which also cross-correlate with all these other things. And we're now trying to see if we can combine lensing and TSE information to understand the distribution of matter in these regions. Yeah, that's it. Thanks everyone for.
Yeah, sorry, go ahead.
Okay. So as far as I know, you need higher electron pressure to interact with CMB more. It's like 10% average, but then if you have more electron pressure in the intracluster medium,
Yeah.
you can actually interact even more.
Mhm.
And in high redshift clusters, we know that, well, we assume that they have higher temperature and higher density.
Yeah.
So they, in the end, they will interact with the
Yeah.
CMB more.
Yeah.
That's expected, yeah.
Yeah.
And then at this point, I was wondering, like, why can't we detect its high redshift clusters already?
Yeah.
If they are, they have more electron density.
Yeah.
And what is missing? I
Yeah.
mean, yeah, if you have any rough
Yeah,
answer to that. And
so-
do you also have any X-ray follow-up studies to look at these pressures, electron densities and temperature maps and stuff like that?
Yes, so the first reason that why we don't have these high redshift things is because our experiments are still noisy. So we just don't have the sensitivity to measure the high redshift clusters. So that's where these future surveys are going to be a real key. Because like you're saying, so we really have to see them, right? If we don't see them, either they are just not hot, or maybe they're partially hot, or maybe something else is happening. Maybe there is just no cluster. Maybe there are just no clusters, right? Could also be there. Right? So we are not there yet. So the highest redshift cluster that we observed is around redshift 1.7 or 1.8, I think. It is actually coming from ACT, I think. But we are getting there. So we will very soon know what's happening, because both SPD3G, CMS4 is a little far ahead in the future, but both SPD3G and SO, just starting around next year, will definitely be able to answer that particular question. And then, yeah, regarding follow-ups, yes. So that's basically so within SPD and within ACT, then so there is like a different working group. What they basically do is they take the candidates and then they do follow-up observations, X-ray, optical, also lensing. Because we can detect all these things, but then one of the key things that we are missing here for cluster cosmology is that we don't have the mass. And we do like follow-up observations with lensing. We do CMB lensing as well. Yeah, so those things are all part of the survey. Yeah.
So in the interest of time, I'm going to suggest folks talk to him after. Let's thank him again, and I'll remind you that as of an hour ago, there was like 1 ± 1 additional slots for dinner. So yeah, thank you, Srini. -5, fine. We will take one. We could also take calendar one, and I'll just deal with Amanda yelling at me that we spent too much money.
That's fair. Oh, I don't.
Well, that means you're.
Good.
Yeah, yeah.
Yeah.